So we resume now with the last section of this conference. And next speaker is Seokbong Seol. He will tell us about formal exponential maps of differential graded manifolds. You have until 1/4 past.
Right. Thank you for the introduction. And thank you for the organizers having an opportunity to give a talk in this hybrid setting. It must be hard to adjust the physical stuff and the online stuff, but it looks like, at least for me, it's been a great experience. So I'm a PhD student of Penn State, and today I'm going to talk about formal exponential map of differential graded manifold, and this work is done joint work with Ping-Xu and Matthew Steiner. Right, so today I'm going to talk in 3 stuff. First part is some kind of motivation or the classical theory involving exponential maps. And then we are going to generalize to something called graded manifold. And then we further move on to something called differential graded manifold of infinite set of exponential maps. Right. So let's start with the first part. So exponential maps arise in classically in Lie theory and differential geometry, especially from the smooth manifolds part. And we are going to briefly look at the exponential maps there. So given Lie algebra, finite dimensional Lie algebra, we know that there is an exponential map. It's a well-known map from Lie algebra to the associated Lie group. And this exponential map is a local diffeomorphism around the origins. What I mean by origin is the 0 of the Lie algebra G and identity element of Lie group. And then this local diffeomorphism induces an isomorphism locally on the differential operators, especially at the origin 0 and the identity element of 1 of G. And then those differential operators, if you look at them, differential operators evaluated at 0 is symmetric algebra of G. And the differential operators at the identity of Lie group is the universal enveloping algebra of G. So exponential map induces isomorphism of SG to UG, but this is a linear isomorphism, it's a vector space isomorphism, and we call this PBW, or Poincare-Birkhoff bitmap. And it has a global formula that is given by this n tensors, n symmetric tensors to this symmetrization. So this symmetrization characterizes PBW. And furthermore, the SG and UG, symmetric algebra of G and universal enveloping algebra of G, they both have canonical coalgebra structures. They both have a canonical comultiplication, and this PBW map preserves the coalgebra structure. Right? If you're not accustomed to the coalgebra, this is the dual notion of algebra. So all those maps are the opposite direction. Okay, so this is the PBW or exponential map on Lie theory. And then we also have similar notion in smooth manifolds. For smooth manifold, we need a connection nabla. And then exponential map, which is defined from the tangent bundle to M cross M, which we can understand as a M cross M as a fiber bundle where the fibers are M. And then we have this exponential map defined as a geodesic gamma. So we have a PDE, and there is a unique solution for when we have an initial vector. So exponential map is defined, and similarly to what we did in the algebra case, we can also look at the differential operators of Tm, but we are looking only at the direction of fibers and evaluating on the zero section. And then what you get is the symmetric tangent bundle. So STM is what you get. And also on the M cross M as a bundle, if you look at the differential operators on M cross M in the fiber direction, so only on the second part direction, and then evaluating at the diagonal section, so then you'll see that the resulting space is again going to be the differential operators on M. So again, exponential map now, which is the local diffeomorphism along the zero section of Tm, will give you isomorphism between these two spaces. Again, this is called Poincare-Birkhoff fit map. And furthermore, this is a bundle map. So induced map is also a module C infinity and module map. So we now have a linear isomorphism of STM and differential operators on M. Also, this can be characterized as algebraic relations. So this is the theorem of Laurent Gengoux, Stinon, and Xu, saying that PBW satisfy these three formulas. So functions are preserved and vector fields are preserved. And then the higher symmetric tensor of vector fields has a formula like this, which involve, if we want to know about the n+1 tensor, all we need to know to figure out is the n tensors. So recursively, we recover everything for PBW with these formulas. And this notion is exactly the same as putting n different vectors, n+1 different vector fields. So these two together with this characterizes the PBW algebraically. Right, so we talked about Lille case and we talked about the smooth manifold case. And then there is a connection between these two. Not only the format is the same, but we also have an example that when we have a Lie group, then when we are only looking at the left invariant vector fields and choose the connection so that left invariant vector fields all vanish, then the PBW is exactly from the algebraic characterization. You see the left invariant vector fields are simply the symmetrization map. So this exactly matches with the Lie case and smooth manifold case. And again, as in the Lie case, we also talked about the coalgebra structure. I didn't mention the co-multiplication in that case, but for this, because this is going to be used later on, I briefly mentioned the co-multiplication. And the co-multiplication basically is given by something called deconcatenation. So if you have n+1 tensor or the product of n tensors, or for the symmetric tangent bundle, or the n product on differential operators, then the way you get is you cut them off in the middle. So the one way to cut them is all of them and one, all of them on one, and the other parts are you cut it in the middle in some sense, with the indexes increasing for both of them. So you can deconcatenate the elements of STM and DM, and that's going to give you a co-multiplication. And you can expect in parallel to Lie theory, with these co-multiplications, you can get isomorphism of coalgebra, which is the PBW map. All right, so there are a few remarks. The inverse map of PBW is something related to something called complete symbol. So this is one characterization, one one thing we can say. And also the PBW, we say that this is a coalgebra isomorphism, so it preserves the co-multiplication. But you see STM and differential operators both have a multiplication, but multiplication is not preserved by PBW. So it's not preserved by PBW. And another thing you can see is this algebraic characterization has an advantage to say PBW, because it does not say anything about the points of manifold, or we don't really need to use geodesic curves, and it only defined using the formulas of recursive formula. So this is one good thing that we are going to use later on to define PBW. Right, so now we are ready to generalize this notion of PBW to graded manifolds. So to start with, we need to define what graded manifold is. So graded manifold is some kind of a generalization of smooth manifolds, and it also involves some Lie algebroid and some other concepts. And the way you define it is we have a smooth manifold, which we are going to call base manifold. And then the data, all we have is the functions. So base manifold together with the smooth functions on M. So the smooth function on M is the global shift of this A. And locally, this function looks like functions on smooth manifold, and the formal power series of a vector space. And this vector space, we understand it as a virtual coordinate. So we have a really existing smooth manifold, and then we have some virtual stuff that we understand to exist, and that two data form a graded manifold. And the prototype of this graded manifold is basically the graded vector bundle. So if I have a graded vector bundle, we are going to understand the function on this bundle to be the section of formal power series of the dual bundle of this graded vector bundle. So that's anything that works with G-graded manifold, if you want to see how it looks like, it's a good idea to look at this G-graded bundles. Right. So now we want to define the PBW for graded manifold. And again, for manifold case, we needed to define a connection. So we are going to also define a connection on this graded manifold. The way we define graded manifold is exactly the same as manifold case, but only the difference is that you have some sign appearing, and the sign appears because we are looking at the graded objects. And so every time you move two things in opposite order, then you see the signs. So you can you don't really need to keep track of signs. You can ignore the sign. And the way the connection is defined is exactly the same as the ordinary manifold case. And then, as I mentioned, PBW, if you use the algebraic relations or algebraic characterization, then without really talking about what the points are and what the geodesic curves are, we can define it. So this leads to the PBW on graded manifold. So given a graded manifold and choice of affine connection, PBW is defined as in these three formulas that is exactly the same as the one in the ordinary manifold case. Only difference is that there is a sign involved. And again, this is because we are looking at the graded objects. it seems like there is a question.
Yeah, I don't understand why you use signs if you interchange. Everything commutes. This is not a supermanifold.
This is some kind of supermanifold.
Yeah, but
So,
then the odd variables, they would anti-commute and not commute.
So that's the Z2 grading. And in our case, it's the Z grading. So it's a Z graded space. So this V has a Z grading. So everything, whenever you commute, then you have a sign.
Okay, thanks.
Yep. All right, so, okay, so this is PBW on this graded manifold. And as in the smooth manifold case, we again have a theorem by Liao and Stinan, saying that this PBW defined on the graded manifold is an isomorphism of graded coalgebra, and the co-multiplication on these are essentially the same as the one I mentioned in the smooth manifold case. Right, so we talked about the PBW on graded manifold, and then we want to further go into the differential graded manifold. Okay, so recall that the graded manifold consists of a base manifold and the algebra of functions, which has the Z grading. And the way you think of the Z graded manifold is you're looking at the Z graded vector bundle, and then the smooth function is given by this formal power series on the section of E. And the additional data, which is the differential graded manifold, is in shorthand written as DG. And the differential is given by something called homological vector field, which is, well, vector fields in this case defined as a derivation on the smooth functions. So we have a vector field with degree 1 where the square equals to 0. So DG manifold is a Z-graded manifold where the smooth function now becomes a cochain complex. And due to Weintraub, Lie algebroid is a good example of DG manifold where given a Lie algebroid, you're shifting it by 1, and then smooth function will be the cochain complex of Lie algebroid cohomology. And then you also have a Chevalley-Eilenberg differential, which will serve as a homological vector field. And in particular, we have two specific examples of Lie algebroid. And one associates with complex manifold. If you have a complex manifold, you have anti-holomorphic tangent bundle of this complex manifold, and you're going to shift it by 1. You end up getting the smooth manifold, which is a space of anti-holomorphic forms. And then on that space, there is a Dolbeau operator. So these two form a DG algebra. So you get a DG manifold MQ as in this way from the complex manifold. And similarly, given a regular foliation by writing the integrable distribution associated by TF, then the TF shifted by 1 together with drum differential form DG manifold, where the smooth function is leafwise differential forms. And this gives you, these two give you a DG algebra, so you get a DG manifold. Right, so we talked about what DG manifolds are. And again, we now want to talk about the PBW map. And what's different is now from the graded manifold to the differential graded manifold, we now have differential inside. And so coalgebras are not just coalgebras, but it also have additional data coming from the differential, and that those are given by LQs. Both of them are Lie derivatives. And on differential operator, you can write it as also a commutator with Q. So with these Lie derivatives or the co-derivations, upon the choice of connection, we have an isomorphism of graded coalgebra from the theorem of Liao and Stinon, that this PBW is a isomorphism of graded coalgebra. But then what about the differential? Does PBW preserve the differential? That was the question. And if not, when does it preserve the differential structure? So that was the question. And if it is a differential graded coalgebra isomorphism, then as in the manifold or graded manifold case, we can call this a formal exponential map of this DG manifold. So that's the whole thing. And to answer this question, we need a notion of Atiyah class. So we are going to define something called Atiyah class. And to do that, we need a torsion-free connection. And torsion-free, again, is the similarly defined up to sign to ordinary manifold case. And then we are looking at a degree 1 section of that eats 2 vector fields and spits out 1 vector field, and is a part of the bundle. So everything is infinity M linear. And this section ATM nabla is defined with this formula, or shorthand expression is that this is you have a LQ on vector field. So the induced LQ is on home of S2 TM to TM, and you apply nabla to this induced Lie derivative. You get the formula exactly matches with this expression. But one thing to keep in mind is that this nabla is not infinity M linear on the second component, especially, for example, f of, remember that this is what we have. So this is different from f of xy. So this means it is not in the tensor. So it's not a bundle map. And why we mention this is because this induced differential, induced Lie derivative, in fact, is a differential on this space. And so we can form a cochain complex like this. And furthermore, this LQ applied to this ATM nabla equals to 0. So this is a cocycle with degree 1. And so we can talk about the cohomological class of it, and is in the H1 of this cochain complex. And it turns out that choice of connection does not affect the class, this class. So summing all this up, we define the Atiyah class and Atiyah cocycle. So when once we choose the torsion-free connection, we have Atiyah cocycle in this space, and its cohomological class, which does not depend on the choice of nabla, will be Atiyah class. And this, by definition, says Atiyah class is the obstruction to existence of the connection, which is compatible with the homological vector field. And this comes automatically from the definition. Right, so now we have something called Atiyah class of a digimanifold, and this is a key to answer the question whether the PBW is an isomorphism of differential graded coalgebras. Before we move on to that part, let's look at some examples of Atiyah cocycle and classes. So if I have a finite dimensional Lie algebra, you have a digimanifold, as in the Lie algebroid case. Smooth functions are going to be Chevalier-Allenberg cochain complex. And then under some choice of connection and some identification on the cohomology, you'll see that Atiyah class of this digimanifold corresponds to exactly the Lie bracket of G. So this Atiyah class is in fact just a Lie bracket for digimanifold associated to Lie algebra. And we also have a digimanifold associated to a complex manifold. And then under some choice of connection and identification, this Atiyah class is corresponding to Atiyah class of complex manifold, which is defined by, which is introduced by Atiyah in 1957. And this Atiyah class of a complex manifold X is the obstruction to existence of holomorphic connection on the holomorphic tangent bundle of X. So this is well-known characteristic classes. And the one we defined on digimanifold applied to the complex manifold, we can somehow recover the classical notion of Atiyah class. In the analogy with the complex manifold case, we are looking at the regular integrable distribution Tm, and we are defining NF as in the normal bundle of this distribution. And then with the digimanifold associated under, again, some connection and identification, Atiyah class of this digimanifold is corresponding to something called Atiyah Molino class of the regular foliation of F. I'm not super familiar with this class, but this has something to do with the obstruction of some kind of projectivity of vector fields. Right. Okay, so now finally we can answer the question that we posed. So we have PBW, sorry. So we have a PBW, and we know that this is a graded coalgebra isomorphism, but when is it differential graded coalgebra isomorphism? This is exactly when Atiyah class equals to 0. So if Atiyah class is 0, then we can say, oh, PBW with the differential is a DG coalgebra isomorphism. And so it happens that Atiyah class is not 0. And we can measure how it fails to be DG coalgebra isomorphism, and it's measured by this, measured by this sequence of maps, R-case. And this R-case, if you look at it, the first term, the R2 is exactly the Atiyah cocycle. Okay, and we also looked at further on our case with, and we figured out that these R case are completely determined by Atiyah cocycle and curvature of this DG manifold and their covariant derivatives. So this is the recent result with Stinon and Xu. And furthermore, well, arcades are complicated to write down as a formula, but if in nice case, when curvature vanishes, then we have a nice simple formula to characterize all arcades. And the reason why we talk about these arcades are because this is a part of some L-infinity algebra structures on the vector field. So the theorem, the previous theorem from Mehta, Stinon, and Xu says that these arcades form L-infinity algebra on the vector field with some degree shifting by negative one. So if you know the notion, then this in fact means L-infinity 1 algebra on the vector field. Okay, so we finally look at some examples. So we have a finite dimensional Lie algebra. Then we again have a associated DG manifold. And then vector fields are exactly the wedge G dual tensor G. Together with LQ, we get a cochain complex of Lie algebra cohomology of G with a joint action of G. And then, and in fact, this cochain complex, in fact, is a DGLA. So it also have a Lie algebra structure, and all other higher terms are vanishing. And so on the cohomology level, you again have a Lie algebra structure on this Chevalier-Lambert cohomology. So this is the L-infinity algebra structure on the vector field. And also, we have a result that in case of Keller manifold, which is a special type of complex manifold, the vector field of the associated DG manifold from the theorem of Mehta, there is a L-infinity algebra structure, and then under some isomorphism, under some identification, this L-infinity structure descends to an L-infinity structure on the holomorphic tangent bundle valued anti-holomorphic forms, which is this space. And on this space, we know that from the classical theorem of Kapranov in 1999, that for Keller manifold, there is a L-infinity structure on this space. And we figured out the one we construct, the L-infinity algebra constructed on DG manifold descends down to the classical one defined, introduced by Kapranov. And the last example is for foliation. Again, we do exactly the same as we did with complex manifold case. So given a DG manifold associated to the foliation, regular foliation, we look at the vector field. There is an L-infinity 1 algebra structure, and it descends to L-infinity algebra structure on the normal bundle valued leafwise differential form of F. So on this space, there also is a L-infinity algebra structure. So this is it for that. This is what I prepared for today. Thank you for your attention, and please let me know if there is any question.
Thank you for the nice talk. Are there any questions? Let's maybe start online. Are there any online questions? This doesn't seem to be the case. Oh. Is there a question?
No, I was saying there is a question from Noriaki Ikeda. You can unmute yourself, please.
I have a question.
Yeah.
Can you mention anything about the integration of a Lie algebroid?
Integration of Lie algebroid.
Yeah, in this aspect.
I I never thought in that. I'm not really familiar with what you mean by integration of Lie algebroid.
In the beginning of your talk, you mentioned about the correspondence with the Lie algebroid and Lie group, Lie algebra with Lie group. And in the kind of exponential map, is it described by exponential map? And the Lie algebroid is described by the graded manifold in. So is it related to, in your work is related to the integration of Lie algebroid to Lie groupoid? No.
I'm not sure about this. I'm not. Yeah, I haven't thought about this direction. So yeah, I cannot really tell you immediately. But we can discuss later on if you want.
Thank you.
Further questions? Also in Vienna? Yes, it's one.
You defined your structure rings of your graded manifolds to be formal power series. Where are you ever needing this? Where do you use this?
Oh, okay. So there are several versions of Z-graded manifold. Some people, especially those who are working more on the algebraic geometry side, they say this is the, they use the polynomial instead of formal power series. But we wanted to use the formal power series because, for example, instead of, let's say, Lie algebra, if I have a L-infinity algebra to start with, we already have a sequence of maps. And then we want to include that case to Z-graded manifold. So it's not clear in this talk why we wanted to have a formal power series, but we want to include, for example, this. Oops. So this, in case of Lie algebra, furthermore, if we start with L-infinity algebra, then what you will need is that formal power series to make sense of the differential, Chevalier-Lemberg differential, because the Chevalier-Lemberg differential would consist of a sequence of maps. So that's basically why we wanted to include a formal power series. Yeah, that's a good point to think about. Yeah.
I have a follow-up question, but isn't that something that the graded Z-graded context takes care of already? So a graded map, like even a degree 0 map between two Z-graded manifolds is Z maps. So that is already an infinite sequence. So I still don't see why the formal power series would be necessary here.
No. We need a sequence of. So, okay. So if we only define with polynomial, then we'll end up not able to include the L-infinity case because of the DCE in this case is going to be the sequence of like a DCEIs. Oh, I cannot write under this. So DCE will be consisting of I equals to 0 to, for example, infinity. And with this, this infinite sum, if you have polynomial on the function side, you will not be able to handle those. In particular, the DC, if you look at the polynomial only, then you'll end up getting, I forgot, probably square may not be 0 or something. Yeah, I kind of forgot. But yeah, so this notion of formal power series was needed to include the interested case of the L-infinity algebra. I'm not sure what the point you're taking, that we don't need the formal power series.
Sorry, nobody else is asking. So is in your formalism like a derivation of your graded ring? Is this a finite sum if you don't use a formal power series? Because in the definitions I think to be canonical, a derivation on your ring can already be an infinite sum of terms, and this includes your differentials. So, well, it's just perhaps a matter of taste how you deal with this. Let's okay, that's the last question. That's my last comment.
Mm-hmm.
Yeah, I think we are remarkably over time, so let's maybe wrap it up here and thank the speaker again.